Hi folks, welcome to this video on simple rules for differentiation. And it's an exciting video because stuff is about to get a lot easier in differentiation. If I think about this function here, if I'm going to differentiate it using lim as h goes to 0 and first principles, it pretty much looks like absolute misery. So let's see if there are some easier ways to approach this. In this video, we're going to exploit 5 properties. That the derivative of a constant is 0, derivative of x is 1. Well, you can just read them here. Instead of proving them, I'll put the proofs in a separate video that I'm working on right now, and I'll end up with a bunch of videos that contain all the proofs for the course. So here are 5 rules. The derivative of constant, c, is 0. That makes sense. If you were to graph y equals a constant, like y equals 2, that's a horizontal line. What's its slope like everywhere? It's 0. So the derivative of a constant term is 0. Let's put that here. All right, next one, the derivative of x. If I were to graph the line y equals x, you'd know that everywhere on that line, the slope is 1. So there's a bit of an informal proof. Here's probably the most important one. X to the n becomes n x to the n minus 1. So if you had x to the 5, it will differentiate 2. The old power comes down front, and the power goes down by 1. Imagine doing that with lim as h goes to 0 in first principles. It would probably take a while. Or even x to the 100. It's no harder now. It just becomes 100, x to the 99. Old power comes down front, and the power itself goes down by 1. We can also figure out what happens if we have a function that has sort of 2 pieces, like it has multiple terms, maybe an x squared and plus a 3x. There's a rule that says that you can just differentiate piece by piece. So it's safe to go piece by piece or term by term. And that's if you have addition or subtraction between the terms. The last one is this. If you have a function that has a constant out front, which we might call a coefficient, the derivative is still going to have that coefficient in it. So this essentially says that coefficients stay. In other words, if I had 5x to the 7, it would turn into 5, and then I do the derivative of x to the 7, which is 7x to the 6. And that gives me 35x to the 6. I'm not writing equals here. That arrow is saying I'm going to do the operation of differentiation. So let's revisit this one here that we cataloged as misery. The rules tell us a bunch of things. So f prime of x is going to be 3 is a coefficient. Coefficients stay. X to the 4 becomes 4x3. Minus 2 is a coefficient here, so it's being multiplied by an x, or x to some power. And the derivative of x, we learned, was just 1. And then this 2 is different. It's a constant term, so it's not being multiplied by x. It's its own term, and that goes to 0. In this example, we've used all 5 of our properties. Derivative of a constant is 0. Derivative of x is 1. Power comes down front. Power goes down by 1. You can do them piece by piece, and coefficients stay. That gives us a final answer here of 12x cubed minus 2. And that expression tells us the slope anywhere. If you want to find the slope where x is 1, you just sub in 1 for x, or any value. Now, before we go ahead and say, oh, well, the rest of everything we've done was a waste of time, it's important to understand that all of the things we're doing here, these properties, they're not just magic. They come from lim as h goes to 0 on some certain cases, and that'll be in the proofs. So everything is held together with the foundation of that lim as h goes to 0 of f of x plus h minus f of x all over h, or first principles. Now that we have some things that come from that, though, our differentiation can go a lot faster. So let's try a few. Over here, y prime, you could pause and try any of these. T cubed becomes 3t squared. The 6 stays. And then for the t squared, we'd get 2t to the power of 1. That's weird, writing a power of 1, but we can do it. Minus 5/3 is a coefficient, so it stays. Derivative of t, well, just like the derivative of x is 1, the derivative of t is going to be 1. This term, the 16 here, is a constant term, so it turns into 0. Lastly, we can just clean up. We get 3t squared plus 12t minus 5/3. Pretty slick. We'll do another one. Y prime here is going to be 2/3 stays as a coefficient. X cubed turns into 3x2 minus 3 stays as a coefficient. X turns into a 1. And you're probably always referring back to those rules as you do it. 4 turns into a 0. We're nearly done. 2/3 times 3 is just 2, so 2x squared minus 3. There's the derivative. In this last one, we might be a little bit nervous with those fractions. So if those look weird to you, you can just turn it into 1/3 x to the 4 minus 2/5 x cubed. So that when we differentiate, we'll get 1/3 times 4x3 minus 2/5 times 3x2. Or, if I make that look a little nicer, 4/3 x cubed minus 6/5 x squared. Now you might be saying, well, could I just have done it over here? I think so. Right? Should it work out the same? 4x cubed over 3? Oh yeah, same answer. And the other one's going to be 2 times 3x squared all over 5. An alternate way to get the exact same answer. We are going to run into situations, though, where division does cause us some issues. So it may be simpler or safer to think about these as coefficients. Either way, whether you're dividing by 3 or multiplying by a 1/3, those stay in the result. So that's great. We're now able to differentiate more easily. That means we can also answer some sort of higher order questions with less work too. So find the x values of the horizontal tangents on each curve. So let's think about this first function. I mean, here it's got y-intercept of 2. It's going to have some sort of minimum somewhere. Where would it have a tangent slope of 0? Well, probably right at its turning point. Now, I don't know exactly where that is. That's just a rough sketch. But the magic on this curve is going to happen at a horizontal tangent. And horizontal tangent means slope of 0. So let's differentiate. I can say y prime, or what did I say, dy by dx here, just to be nice. 4 stays. This turns into 2x to the 1. Minus 3 stays. It's a coefficient. Times derivative of x is 1. Plus 0. And we end up with this. This is the slope anywhere. We want a slope of 0. So we sub in 0, not for x, but for slope. dy by dx, or y prime, that means slope, or the instantaneous rate of change. So we can just get a little equation. 0 equals the derivative, and solve it. I'm alleging that on this function, you'll get a horizontal tangent at x equals 3/8. Let's check it out on Desmos. There's the function. It's going to have that horizontal slope right at its turning point. Let's see if we can find the x value. Oh, it's 0.375, which is 3/8. So if you got the idea for that one, you could pause and try the next. On this curve, whatever it looks like, the magic is liable to happen at those horizontal tangents. So let's see, this is going to give us y prime. Maybe I'll just play it safe here and call that divided by 3 a 1/3 x cubed. You don't have to. but it's going to make me feel a little safer when I find the derivative. So 1/3 times 3x squared minus 2 by 2x to the 1 minus 6 times 1 plus 0. Okay, just using those derivative rules. Where y prime is x squared minus 4x minus 6. Again, we want a slope of 0. So put in 0 for this. And you can try and factor it. I don't think we'll have any luck. So in that case, we'll have to use a quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. And I'm going to put this in. 4 plus or minus b squared. So that's negative 4 squared is 16 minus 4ac all over 2 times a, all over 2 times 1. So 4 plus or minus the square root of 40 over 2. I'm okay with you leaving it like that, but it might be nicer for us to write it like this. That's 4 over 2 plus or minus the square root of 40 over 2. And that can simplify even further. 4 over 2 is 2. Root 40 is root 4 times root 10, so it's 2 root 10 over 2. So in simplest terms, it would be 2 plus or minus root 10. Or you could get the decimal approximations. If you go and graph the original function, I guarantee you at those places, which are about 5 point something and negative 1 point something, you're going to find horizontal tangents, or you're going to find turning points on the curves. One last one. We're going to find the x-intercept of the tangent to this function at x equals negative 2. That's a lot to process. Okay, so the x-intercept of the tangent. I'm just going to draw a function that, I know, it has nothing to do with this particular one maybe that we have, but there's a cubic that's negative, and I'm just going to imagine that there's negative 2. If I draw in the tangent, maybe I'll put it in red here. There's the tangent at x equals negative 2 on some function. I'm looking for this kind of point. So there's a lot to unpack here. But I think it's clear that you're going to have to know the equation of that red line. You're going to have to know the equation of the tangent. And in order to find the equation of the tangent, you'll need to know the point and a slope. We've found equations of tangents before. So the point is x is negative 2. The corresponding y value would come from subbing in negative 2 into this. If you want a y value, plug into the function that says y equals. So that's going to give us negative 8 times negative 2. So 16 minus 10 plus 1, a y value of 7. I'm going to get rid of this rough sketch. And I'm going to start working on finding slope. And to do that, I'll differentiate. Yes, I could use lim as h goes to 0, but it's going to take forever. So the slope anywhere is just negative 6x squared plus 5. We don't want the slope anywhere. We want the slope at x equals negative 2. But it's easy to find that derivative function and then just sub it in. So the slope at negative 2 is going to be given by this, which works out to be negative 19. Now we have enough stuff to find the equation of the tangent line, or of the tangent at x equals negative 2. We'll use the point-slope formula, and we'll carefully sub in. So y minus, here's x1, y1, so y minus 7 equals m, which is the slope, x minus negative 2, so x plus 2. And you can not convert forms. It's really up to you. I like to see my lines in y equals form. And I get this. And this all seems wildly abstract to this point. So let's take a look at what we found on Desmos. So here's the original function that we had, or at least part of it. It continues on forever. And here's the tangent that we found. Does that really look like the tangent at x equals negative 2? I think it touches right there. What we're wondering is, what is the x-intercept of that blue line? And I mean, I can get the Desmos to figure it out here. But we might be asking ourselves, well, how can I do that analytically? If you want an x-intercept, you sub 0 for y, because on the x-axis, y has a value of 0. So if you want an x-intercept, we sub 0 for y on this tangent line. And we just work this through. 19x equals negative 31. X equals negative 31 over 19, which is a more perfect version of the answer than what Desmos found to 4 sig figs for us. So now we have quick ways of finding derivatives, which is excellent. For practice, we can take a look at page 124, the questions that are listed here. There are a few for fun ones as well. I hope that you found this video useful. Good luck with the material, folks, and take care.